We're continuing the lecture on the sound chapter. Today we're gonna see some further discussion about the how to measure the speed of sound. There are two methods for this, and then we're gonna see some discussion regarding properties of sound and reflection drawing. So measuring the speed of sound, the topic we have. Measuring the speed of sound in air. The first way we have is what we call the echo method that we discussed in the last class. The process is very much similar to the very last figure that we had seen in our last class, which is something like this. We use this exact similar scenario, but what is important for this mechanism to work, we need two people, one to make the sound, one to make the observation. So for this process to work, there should be one person standing in front of a large reflective wall, can be a building, can be the boundary wall of some wall, and there should be empty space in between. This person should have two pieces of wooden block in their hand to make sharp pulse sound. Important property. This is the phrase by which we define it. So a student holding two pieces of wooden blocks who is gonna clap together to make sharp pulse kind of sound. So not sounds, not continuous sounds like or like ringing a bell continuously, nothing like of that sort. We're gonna make clap kind of sound, and the gap between the person and the wall should be preferably more than 20 meter. So last class we have seen that for air, the distance for the echo to be individually detected, the distance should be more than 17.5 meter. We are now recommending a distance of more than 20 meters so that the echo is definitely individually heard. So more than 17.5. So it can be, if someone says this should be more than 25 meter, that's also okay, but it should not be definitely less than 17.5. That is the lowest distance between the observer and the echo should be. And there should be another person standing in the same alignment. There should be another person who should hold a stopwatch in their hand. So this is the wooden box. So student 1, student 2 holding a stopwatch. So you can actually make it look like a stopwatch, or you can just label that this is a stopwatch. So the way this experiment will work, we would want to make an observation that the sound should travel from our observation point, which is this line, to the wall and back to our observation point continuously, because we want to measure the sound continuously. So one of the examples that I can put in this case, that whenever we measure the sound for simple pendulum, whenever it's making some oscillation, let's say a simple pendulum is hanged by a thread from a fixed support. If we want to measure that, and let's say we set it into oscillation like that, it is undergoing some oscillation around these two ends of the simple pendulum. The way we measure the simple pendulum's oscillation time period is that we start observing the motion, and then we measure the total time it takes to make 10 oscillation. This is the typical number that we prefer. At least 5 is okay if we want to save time, and to get better accuracy, at most 20 is also okay. That is also allowed, but we don't go for more than 20. We don't go for less than 5. So we see 10 oscillation. It means that, let's say the pendulum is swinging by left and right. At one point of motion, when the pendulum would be somewhere in the middle and going to one of the sides, we're gonna sync our hand motion with the pendulum, and then we're gonna press the stopwatch, and that should set the motion of the pendulum like that. And then we should count. For example, if we press it whenever it's going over here like this, and if we press the stopwatch at one of this uh, motion, then this is our t equals to 0. So when the pendulum completes one goes to the all the way to the right, goes then all the way to the left, and then once it reaches to here, these are 1 time period. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, and then when the pendulum finishes up over here, we stop the stopwatch. That practically gives us the amount of time it takes for 10 oscillations. Now, so 10t equals to the amount of time we calculate from the stopwatch. So time period will be given by the amount of measured time divided by 10. That gives us the time period of the pendulum. The reason we prefer to calculate more than 1 time period, the reason we prefer to observe more than 1 time period for any measurement, I mean, you might wonder that why is it not that we are only measuring the time period for only 1 oscillation? Why is it important that we have to measure it for 10 oscillations? Why is that? I mean, why multiple readings have to be done and then we have to divide by 10 to get the average reading? And the reason is that we human beings have a thing that is called reaction time. So reaction time is a natural source of error that we human beings include in any measurement of time if we are not careful. It's related to the nervous system and the muscle system of our body. The idea of reaction time is that the amount of time our body takes to react to something, which means, let's say you hear or see a physical input at which you are supposed to perform an action. The way this whole thing works is that sensory input, a visual input or a auditory input, goes into our brain, gets processed in our brain, sends some signal to our muscles, maybe to the muscle of our hand, to start the stopwatch or stop the stopwatch. And after we press the stopwatch by contracting our muscle, then only we actually have the stopwatch getting started or stopped. This process of from the point of receiving the signal, auditory signal, audible signal, or visual signal, and then actually being able to perform the action that we want to do actually takes some time. For a regular human being, whenever I say regular human being, I mean that the person is sane, adult, and not intoxicated, that kind of a person, well-rested person. For a regular person, the reaction time is approximately 0.4 seconds. By doing practice a lot, it can be reduced to less than that, but reaction time will always affect our measurement. The reason we prefer to do more than 1 oscillation is that whenever we make any measurement of time, the total amount of time that we measure can be errorful by up to 0.4 seconds. You don't have the idea of uncertainty in your syllabus yet, but I'm trying to explain to you why this is important. Other than measuring, so whenever we measure the time for 10 oscillations, the actual time that we calculate out of the stopwatch would be 10 oscillation plus or minus 0.4 seconds. So our reaction time, human reaction time, is going to add some error to this measurement. Now, I have written only 0.4, but this would be actually more than 0.4. I'll tell you why. What you need to understand that whenever the stopwatch will, whenever the pendulum will move back and forth, we have to do 2 observations. First, we have to start the stopwatch at the instant of our defined starting point. So we might make 1 error while starting the stopwatch, and when the 10 oscillations is done, as the pendulum crosses by the same starting position in the same direction, after 10 oscillation, we have to stop the stopwatch as well. So we are going to perform 2 actions. Our muscle nervous system should perform 2 actions: starting the stopwatch and also stopping the stopwatch. This brings up a significant amount of error. So actually, the amount of error that we could possibly do is actually 0.8 seconds, double of that thing. You don't have this concept in your syllabus yet. It's in your AS level. I'm just trying to show you, to give you a understanding why is it necessary that we have to measure multiple oscillation time. So এই এররটুকু একটা স্টপওয়াচ মেজারমেন্টের সময়, একটা স্টপওয়াচের মেজারমেন্টের সময় আমাদের এই এররটুকু এমনিতেই হবে। এখন ইন্টারেস্টিং ফ্যাক্টরটা হচ্ছে, আচ্ছা আমি একটু এখানে ইকুয়েশনটা ভুল লিখছি। মনে করো আমরা 10 অসিলেশনের টাইম মেজার করলাম। সো 10 কি ইকুয়ালস টু হচ্ছে, মনে করো টি মেজার করলাম, এটা হচ্ছে আমাদের মেজার টাইম ফ্রম দ্য স্টপওয়াচ। This measurement can be errorful up to plus or minus 0.8 seconds because of the human reaction time. Now, whenever we have 10 oscillations, if I divide this duration of time by the number 10, we can get the oscillation duration for or time period for one oscillation, which we call time period, is equal to t divided by 10 plus or minus 0.08 second. Now, what is important, because we chose to observe 10 oscillations, the amount of error that we have over here is actually significantly less. It is 0.08 second. Whereas if we observe the motion for 5 oscillations, then the equation would look like this. Have a look. Then it should be 5 oscillations should be equals to the amount of time that we measure from the stopwatch. Let's say I'm gonna write this with t prime, because this time and this time should not be equal, obviously. So that is that plus minus 0.8 second. So every single measurement of time that you take from start to end, you're gonna make typically about 0.8 second of error. That's human reaction time. So in that case, the time period measurement would be equal to this measured time t by 5, t prime by 5 plus or minus 0.16 second. And if we take more than 10 oscillation, let's say if we observe 20 oscillation, for example, in that case, the duration for 20 oscillations would be equals to the measured time from the stopwatch, maybe t double prime. I'm trying to represent a different amount of time, plus or minus 0.8 second. So that way, the one measured time period should be equals to t double prime divided by 20 plus or minus 0.04 second. The point that I want you to observe is that our reaction time is going to affect one observation once in the start, once in the end, no matter how long we measure it for. So if we measure the amount of time for a longer duration, for example, whenever we are trying to observe for 20 oscillation, the ultimate effect of error of our human reaction time is becoming on our actual one time period is only 0.04 second. That's actually quite small. Compared to that, if you go for 10 oscillation, this is about 0.08 second. If you go for only 5 oscillation, it's about 0.16 second. You can see that the bigger number that we go for, the bigger number of oscillation that we observe, this amount of error that we are susceptible to do, which is 0.8 second plus or minus, this would be distributed over all of those numbers. So here, what essentially happened, this is actually 1/5 of 0.8 second. This is 1/10 of 0.8 second. This is 1/20th of 0.8 second, which means the more oscillation that we observe, our human reaction time related error would be distributed across those observations uniformly. So we're gonna have less error for the measurement of one time period within our calculation. That's the whole point why we prefer to observe more than one oscillation. The more the merrier, usually that's true. That's why the maximum, but if we want to take too much time to make one single observation, this might actually cause in a much longer duration of time requirement for the whole experiment to perform. That's why for a lab experiment, the maximum number of repetition that we allow for CIE syllabus is 20, and for statistical approach, the minimum that we allow is 5. Typically, we go for the halfway point. We can go for 10. If you wonder that, sir, what if I want to go it for 12, or if I want to go for 15, can I do that? The answer is yes, you can do that, but these are not very common. So examiners don't see that very often, and we don't recommend the students to do that either, because this going for a 10 oscillation actually makes the calculation much too simpler, as so you don't have to use a calculator to do the division. Simply remove the decimal point a little bit to the right, one place to the left, not right, to the left, and that gives you a calculation. This is the reason why we want to do multiple observation for a certain time measurement. Does this idea make sense, that why we are trying to get more observation of time period rather than only one time period observation? Does it make sense?
Yes, sir.
Yes, sir.
Yes, sir. So that's that. So similarly, what we're going to do over here, we're going to do a similar scenario over here. So we're going to physically try to achieve that similar instance, that we should clap this two pieces of two wooden blocks in such a way that sound should be traveling forward and backward continuously, which means, let's say we're going to make one clap. The first clap happens, the sound goes forward, and then it reflects off that strong wall, vertical wall, and comes back, and the echo is heard. So the hearing is actually done by this person. This person is hearing is also done by this person. This person is responsible to make the sound. This person is supposed to measure the time, because the sound has to be made by two sources. So it would not be very recommended if we have only one person to do the experiment. So once student one, let's say this is student one, this is student two. Once student one hears their echo, they're gonna do their clap again in such a way that the student one will try to match his clapping at the exact time the student hears the earlier echo. Student one will try to create the echoes, create the claps of the wooden blocks in such a way that he makes one clap at the exact instant he hears the echo of the earlier sound. Let's say there is a clap sound. So let me give an idea. Let's say clap, and then you hear just a fraction of a second later you hear the echo. The aim of student one is to do one more clap exactly at the instant the echo is heard, which means he is gonna try to perfectly overlap the incoming echo. So what this will ensure, it will ensure whenever the student makes the first clap, the first sound goes by and first echo comes in. First echo is heard, he makes the second clap. Second sound goes by, second echo comes in. He makes the third clap. Third sound goes by, third echo comes in. So if he continuously can manage to do that he is making those wooden claps in such a way that every clap is perfectly synced with the sound of the earlier echo, we can make sure that for that synchronized clapping, sound is made to travel from the clapping location to the wall continuously back and forth. We can make sure of that. এই পার্টটা কি বুঝছো বলবান?
জি স্যার।
ঠিক আছে? So this is the important bit. This is what student one is responsible for. Once the student actually achieves such a scenario that he is making the claps and the echo is not heard anymore because all the new sound is made at the exact instant the echo is about to heard. So the echo, the following clap is perfectly matching with the audio or with the hearing of the previous echo. So once the student achieves this person, student 2, will then start their stopwatch at a certain clap number. So if the student starts their clap number at, let's say, t equals to if the student let's say gives a clap and then count 1, that would mean one time amount requirement should happen. Actually I should draw this thing from here to here. Drawing a second student actually sometimes is not done. If you look up in your figure, they usually you draw only one student, but we need 2 students to perform this experiment. That's why I drew student 2 as well. But my point is that the student should, let's say the student 2 starts the stopwatch and counts 1 for one clap. When the student will count 2 for the next clap, the sound has actually covered back and forth one time. So between counting 1 and 2, we have one amount of time that the sound has traveled back and forth. Between counting 2 and 3, the sound has covered another time back and forth. Between counting 3 and 4, the sound has covered another time between the source and the back and forth. It has covered the distance back and forth 3 times. So the reason I'm trying to show you in this manner is that whenever the student counts a certain number, the actual number of traveling for the sound is 1 less. So if the student has if the student stops their stopwatch at the count of maybe, let's say, 10, the actual number of times that the sound has traveled back and forth is actually 9 times. Do you understand this point? Because the moment he counts, because he's starting his count from 1, so sound hasn't yet covered the distance 1 time. The moment he counts 2 for the second clap, sound has actually covered the whole distance in between 1 time. Between the counting of 1 and 2, there is 1 time. So if he does the counting in this manner, then if he wants to get a total of 10 times this back and forth, the final number should be 11. When he so he should stop the stopwatch when he counts 11. That way, in between 1 and 11, we should have 10 gaps, or we should have whenever the student counts up to 11, he should have 10t. But if he counts only up to 10, he's gonna have 90. He's gonna have one less. Do you understand my point?
Yes, sir.
If the counting starts from 1, then the ending should be 10 more. Vice versa, if student 2 starts their count from 0, let's say he observes the sound, and then he, for one specific sound, when he's about to start the stopwatch, he says 0 and immediately presses the stopwatch. In that case, he can actually count the exact number. So 0, 1, 2, 3, 4. If he goes this way, then if he counts all the way up to 10, that would also still give him perfectly 10 times the sound takes to go back and forth. So important observation, if we start counting from 1, we need to count 1 more so that we have 10 gaps in between. If we count from 0, we can count up to the exact same number, because we should have that exact equal number of gaps in between. So that's the counting process. In this process, we're going to measure how much time it takes for the sound to go back and forth, at least for 10 times. 20 times is also good. If we want, we can do that. So we do that. So let's say we have measured our first observation of time, let's say t1, for 10 times the sound time it takes for the sound to go back and forth. What we're gonna do, we're gonna do, for the sake of better experiment, we are gonna record this time for our first experiment, for our first observation. Then we're gonna repeat the experiment, let's say 2 more times. So we're gonna do the same exact thing and come up with 2 more time amounts, t2 and t3. So we're gonna measure the 10t amount of time 2 more time. Now, ideally, you should think that for a very perfectly executed experiment, all of these time amounts should be exactly equal. But for a practical case, it's not going to be equal, because we are susceptible to errors. That's why, to overcome these errors, or to minimize these errors, actually overcoming these errors entirely is statistically possible, but not for observation, only for 3 observations. So we say, to minimize the effect of these errors, we are going to measure this amount of time it takes for the sound to go back and forth 10 times. We're going to measure it 3 times. And then we're going to make an average of it. So let's say the total amount of time it takes to go back and forth, 10t should be equals to t1 plus t2 plus t3 divided by 3. That gives you the total average time it takes for the sound to go back and forth. And then we simply calculate the amount of t, which should be t1 plus t2 plus t3 divided by 3, which is basically the average time divided by 10. This is the amount of time the sound takes to go back and forth 1 time. So back and forth is included within the discussion in every single case. Then comes a very simple equation. We can measure the distance in between. Let's say if we have gone for a 20-meter distance, we use 20 meter. If we have gone for 25, we use 25. We shouldn't go, actually, one thing you should understand, that if we make this distance pretty big, the bigger we make the distance, there will be longer gap between the made sound and the heard echo. So the bigger this distance, sound would take longer time to go forward to get reflected off the wall and eventually be heard by student 2. But that also brings about a second problem. The longer the sound has to travel, the dimmer it's going to become. It means when on the receiving end, it is going to become much too quieter to hear, because the sound has to travel a much longer distance going forward and backward as well. So it's going to lose energy to the atmosphere by means of vibration of the particles, which actually dissipates out in the form of heat energy. So if we make the distance really long, or let's say significantly longer, this student has to do their clapping really hard, which might be too much labor intensive. So performing 3 different three times the observation might actually prove to be difficult. So, and also if we make the distance too small, the difference between the made sound and the echo cannot be heard. So there is a sweet spot between these two. So the distance cannot be distant from the source and the reflector surface cannot be less than 17.5 meter. That's what we established in our last class. So anything bigger than that is okay. So going for a measurement of slightly bigger than 20 meter is actually pretty good. It doesn't challenges the audio hearing of the echo, because the volume doesn't get that much low, and also the amount of time it takes from the made sound to the echo hearing is also workable. So that's basically the idea, that why do we prefer to write d slightly bigger than 20 meter, or if you are if you want to give a specific number, you can say that both the students stand 25 meter further away from the wall, or maybe 22 meter further from the wall, or you can write exit 20 meter further away from wall, so that you can directly propose that amount of distance as well. That also works. And then we can go for the equation that we know, v equals to 2d by t. That's the equation for the for echo. So in this case, we can place all the numbers. You will gonna measure the d. And if you're actually proposing how to do this experiment, you should mention each instrument which we should be used to measure each variable. So in your account, whenever you're writing the answer for how this process should work out, echo method, you should not only write we measure the distance d between the observer and the wall. You should rather write we measure the distance from the person, from the observer to the wall, using a meter rule, or you could also use a measuring tape because we are measuring a pretty long distance over here. Or we can use a turtle wheel. Using a turtle wheel might not be a good idea because we have a flat surface at the end. So I think a measuring tape is the most appropriate instrument for this measurement because it's quite large and we say linear distance. So measuring tape can be used. Measuring tape can be also used for curved distance as well, but in this case we have linear distance. So I think measuring tape would be pretty nice. Point that I'm trying to make, if you are trying to propose that we're going to measure the distance, you have to mention what equipment are we going to use for that. So mention that, and then we place all the numbers that we calculated from our experiment, and that basically gives the speed of sound of the through air for that instant.